fast. Hold on, budget update. Let's get through it.
Oh, okay. Well, it's only AELS tangential, but this is just for the SE exams. There was a recent webinar where they talked about the changes that they're going to make. But long story short, in April of 2026, the test will effectively be 30 to 50% longer for the questions, and they're doing it by adding time and by reducing the number of unscored questions. So they have a bunch of unscored questions that they put into the test, see how people do, and then next year, they'll put it in if the questions turned out well. So they're going to reduce that, increase the time, because there's been a lot of complaints about everybody being rushed on the depth sections.
Thank you, David.
Okay.
Finance update.
So currently we have in our bank account $16,082.97. Upcoming additional expenses that we have this year is just our Square website fee of $20. Otherwise, appears that all our expenses for this year has been paid. But since it's coming, then we're going to be, starting to collecting the membership for the next year. So we are inviting people to start planning and renew the membership. Also, I wanted to add for anyone who paid for lunch, and if you need a receipt for reimbursement, just let me know and I can write that receipt for you.
Thank you, Magda. Corporate sponsorships include 2 memberships. So if you have a company with multiple people, you do a corporate sponsorship, and also you get a banner on the webpage, email. So, all right, with that, we're going to hand it off to our presenters that you've been patiently waiting.
All good. Thanks so much. My name is SEAAK History. I'm with RWDI. Thanks so much for having us. Looks like a nice turnout and extra tables. So that's great. I'm a project manager with RWDI. I'm based out of our Portland, Oregon office. I got 2 of my colleagues here. One is Kenny Yu. He's based out of our office in Toronto, or Guelph, which is outside of Toronto. It's a little small city. And also John Kilpatrick. Kenny works in our snow and ice division, so he's going to be talking mostly today. And John is one of our leaders for our wind engineering work. So might add a few things in here as well. So I'm going to give us kind of a brief overview of what RWDI is, so that folks that have never heard of us, or maybe who has heard of RWDI? All right, us maybe, so that's good. Not completely blind, that's good. Next slide. So we're an international firm. We have about 800 engineers worldwide. We're about 50 years old, about 52 now. We have offices all over the place, primarily in North America, but we also have offices in Europe, Asia, India, and Australia. And we do a whole host of different types of specialty engineering services, mainly all around how does our natural environment affect the built environment, or vice versa, right? Next page. So this just sort of gives you an idea of where our offices are located by the little pings. And then it's hard to tell in here, but there are countries that are bolder or darker than the other ones. And that just are all the different countries that we have had projects in, right? So we have had projects pretty much everywhere on the planet, which is kind of fun because they have different climates and different challenges in each one of those places. Next slide. This is just some of the fun, cooler, like, modeling and lab type stuff that we get to do at RWDI. The first image is one of our wind tunnels. So we build physical models of buildings. We build the surrounding building, and then we put them in our wind tunnel and test them. We sometimes introduce smoke more as a visual tool, so you can see what's going on, because can't see wind typically, right? So this just sort of helps mostly our clients understand, like, when they're like, why is wind doing this weird thing here? Why do we have pressures at this weird corner? Well, we can show with some smoke to kind of help represent that, right? We also have a lot of new digital tools, which has been super helpful. The code doesn't let us always use them, but they're super nice for informing things. This one is specifically around pedestrian level winds and that kind of thing, which isn't code, but it's more for comfort and other things, right? And then on the right is some snow related studies that we have a water flume where we put basically glass particulate into a bucket of water and run that, and it will drift. So basically snow in air is similar to sand in water. as far as how it falls. So we can do snow drifting studies basically inside of a water flume. We also do a whole lot of solar panel arrays and things like that. And then Kenny's too fast for me. But maybe it'll come back. It is on his computer. Anyway, on the bottom right is our water flume. So just some cool tools. And then this slide, really hard to read for you all. I call this our Wheel of Fortune, but essentially it's all the different service areas that we offer. So we have a lot of wind and snow stuff. We also do a whole host of sustainability type work. So like energy modeling, green certifications, guiding principles type stuff, or even energy modeling and commissioning type work. We also have a full noise, acoustic, and vibration team. So building acoustics, vibrations from structural vibrations, also acoustic vibrations. And then we have a full enclosure consulting arm as well. So think the exterior of the building, all 6 sides of the box. How do you keep the building warm and dry? So that's what that team specializes in. So a whole host of different types of things, again, on how the natural climate affects our built environment. And I'm going to hand it over to Kenny to get you into the excitement stuff about snow. Oh yeah, I forgot about this slide. We just added this. This is just a few of the projects that we worked on the last few years here in Alaska, just to kind of give you an idea that we work in the state, right? You guys were talking about bridges earlier, so we've done a whole host of bridges as well in Alaska. So it'd be fun if you added some wind dynamic pressure to your testing instead of just structural loads, or forces down. Maybe get that on the next year, right? Anyway, next slide. Thanks.
Yeah, so today we've prepared this, I guess, 1 to 5 sections to talk about snow and ice. And then the first, I think, is probably should be the most interesting to everyone sitting here. It's really how things have changed from ASCE 716 to ASCE 722, because we've seen some major updates on the snow loading provisions. They're basically trying to make a step forward to make, more realistic predictions on both how the ground snow load distribute across the country, and also how the snow loading distribution will realistically form up on the roof pieces, right? And then it also tries to address the uniqueness of your local climate and also your roof thermal performance. I think I'm just going to dive right into this first section here.
I can barely hear you, and I'm sitting in front. It would help if you stood up.
Okay. All right. So is everyone okay to hear me right now? So the first one is probably the biggest change that was brought to the 22 version of the code. Is so when we're trying to figure out the ground snow load for a city in the older version of the code 716, it's really just one zone map for the snow load with you've got a set of scaling ratios to scale the value from that map to the different risk categories. And that ratio doesn't really change, depends on where you're located, right? And in the new version of the code, so the researchers have tried to look at the ground snow load distribution across the country on a risk-based analysis. It's basically, you've got a set of contour map for different risk category, and they're really trying to target the probability of failure due to snow loads in different regions, and is really trying to, and the values from those contour maps are actually your ultimate snow design value. So you don't really have the combination factors when you're trying to do your calculation. When you find in the 716, I believe it was at 1.6 for the snow load, and you no longer have that in the 722 version, just because it's all baked into the map right now. And really based on the observed snow load record and how it fits into your extreme value analysis model, you would have, I guess, increased load in some regions and decreased load in other regions. And in general, we've seen a reduction in heavy snow regions, and then also increase in regions with relatively lighter snow. So with that said, I mean, that's all good. And then the hope is just to bring in a more realistic approach of looking at snow load across the different areas of the country based on different level of risks. And also you can see from I'm not sure if it's quite clear here, but I think at least in the older version, there are a lot of areas marked as case study areas. Those are basically those mountainous regions where the snow load would change drastically with your elevation, right? And then, but in the newer version, that aspect has been addressed, and then you no longer have a CS area anymore. You can really just go to the ASCE has a tool, basically punching your lat long, you would get a code snow load value right away. So that is the case for the continental US, but not for Alaska. Unfortunately, we're fortunately. But so far in the 7.22 version of the code, what the code has done for Alaska is really just to bake the 1.6 factor into the values directly. So for example, for Anchorage, you have 50 PSF before for, I guess, a risk category 2. Now you're just having a 80. That's a straight up multiplication of 1.6 there. But what I heard is that the risk-based approach for Alaska has been proposed, and I think successfully it should be coming up to the 28th version of the code. So I guess keep tuned for that. And the other big thing that was brought into the 22 version of the code is what we call a winter winds effect. And this is, so previously we looked at how the ground snow load is distributed across the country, right? Right now we are looking at how snow is actually going to accumulate and distribute on the roof, on the building roof. So previously, if we are calculating the drift surcharge on a what we call a stack or a wall between a upper and lower roof, it's purely a function of the fetch length of the upper roof with your PG, which is your ground snow load. It doesn't really matter how windy it is in a specific city, because you can probably imagine that the windier you get, there's a better chance for wind to push the snow towards that step, essentially forming a larger surcharge, right? So that behavior has been addressed in the newer code, which a winter wind parameter W2 is now introduced, which means like in the lower winter wind region, we've got a reduced snowdrift, and which is a lower W2 value, and in the higher wind region, we've got a higher W2. That means the calculation for your drift height will be increased for those areas. And on average, if we're looking at W2 that's close to 0.5, that means it's basically very minimal change from the previous code. And if you're looking at Alaska specifically, one thing I noticed that so I was looking at this winter wind parameter map for the continental US, and I think the W2 value ranges from something like 0.25 to as big as maybe 0.65. So, but in Alaska, we actually have a W2 all the way from the lower range of 0.1, which I think was in Fairbanks, all the way up to 0.8 to or 0.9. What that means is that we've got this really drastic, I guess, difference across the state, where we have cities with the really low winter wind speed, so not really able to push the snow on a flat roof towards the steppe region, forming a big drift. But we also have regions where we get, I guess, crazy winter wind, and that's forming really large drifts. I tried to do a quick calculation for, I guess, some of the major cities here for Anchorage, and both for Anchorage and Fairbanks, we're looking at relatively low W2 values, where we actually would see a reduction on the drift height calculation. I was a little, I guess, curious about that before I came here, because those values do mean a really low wind speed, and at least we were just in Fairbanks for 2 days before this. there's basically no wind at all. And here in Anchorage, I think it's a little windier than Fairbank, but still, I would say it's relatively calm in terms of how intense the winter wind is. Yep.
So does this winter wind effect take into account the duration snow is on top of roofs as well? Because, obviously in Alaska, snow is on roofs for much longer. So even though the wind could be lower, that roof is, has 6 months of wind on it not 6 months, but, to form up a drift.
Yeah, so I think you're talking about from the whole winter
Yes.
perspective, which I don't think would be necessarily touched by the code, because I think at least from what I've read, the research is only down for a different wind speed, how much drift can be carried towards that specific step. If we were trying to understand what the past, I guess, climate time history would do to the snow formation on the roof, then we'll have to use more advanced tools like maybe physical model study and combined with the climate data to do that. But at least for code, I don't think that's necessarily accounted for different part of the country. I think from what I've read, it's only purely based on the intensity of wind. Yeah.
Your chart for acreage, you have 3.5 for ASCE 716 HD and then 1.3 feet for 722. I'm assuming those are both HD values. Can you directly compare them if one's based on a service ground load and one's based on an ultimate ground load?
So those are all of the ultimate design snow load for structure, not your service level.
So
No,
the
yes.
HD in the case for 716, that's you turn that into an ultimate HD.
Oh, okay. So you're saying
Just talking about the HD.
right. Yeah. So that has been factored by the one. So in the 716 version, that has been factored by the 1.6 factor there.
Six to try and get
Yes, and then in the 22, because it's straight up ultimate from the PG already, right? Yeah, so I was also surprised to see such a difference, at least for Fairbanks and Anchorage, but for areas like Bethel, you've got I guess supposedly much higher winter winds. It's actually, you're gonna end up having a higher drift than the older code.
what is the Bethel W2 just for?
I think it's 0.8 right here, if you can see my cursor here.
0.7.
0.7.
Got a 0.8 at Cold Foot or Cold Bay.
Yeah, so for those areas, we end up having a higher drift component than the calculation from the older version.
Another thing that I've noticed as I've looked through this standard is that the density equation has not changed, but our balanced snow loads and ground snow loads have increased by a factor of 1.6.
Yeah, so
So I don't know that this was the intent, but there's in Anchorage, for instance, the 28-inch step will not generate a drift. A 29-inch step will. With this new code, the amount of step that will or won't generate a drift increases by a significant amount. You'd be able to have a 3-foot step and not have to apply
Yeah.
a drift to it.
I
So
think,
it's an advantage that we're getting as engineers, but it also just makes me wonder, like, is this an unintended consequence that they had? We put parapets up on buildings a lot of times, like, oh, you can't go that high because then there's drift and we have to reinforce the roof frame. Well, now it's like, oh, this code just bought you,
Yeah.
10 more inches.
I think, so I think that's one of the questions I had as well, is when I was looking at comparing the density calculation between the two versions, they're basically the same, but then from the new PG, we have the 1.6 big thing. That basically means, yes, when you calculate your density, you've got much denser snow for the same area, which basically decreases your snow calculation, right? So that's unfortunately, I don't think that's something I can answer right now because I don't sit on the SEAAK committee, but I think that's a really valid question that I also had.
Yeah, it's good.
I do
What-
sit on the committee, so I can try to handle that. This is Mike Gibbons from RWDI. Sorry I couldn't be there today. So I think the intent is that previously you would calculate your drift height and then you'd apply your 1.6 load factor, and then the effective drift height goes above the obstruction. So this is in some ways actually intentional in that now when we have drifts, they're only drifts that are going to be going up to the top of the obstruction after all the factors are being applied to it. So this was one of the things that comes out of calculating things at your sort of so-called ultimate return period or fully factored ground snow.
One thing I'll add, so I sit on the ASCE 7 wind load subcommittee, and there are definitely inconsistencies in the code from time to time. And despite there being dozens of people involved in reviewing these things, sometimes it might take somebody doing a calculation in a particular region to identify a problem. So when you see something interesting like that, your first thought might be, well, maybe I'm crazy or maybe I've done something wrong. But I would say, like, encourage you to ask a question of the task committees responsible for snow, or if it's a wind issue for wind, because there are every single query that comes in from industry or even the public has to be addressed by the subcommittees. And in fact, some of the code changes occur because there's been questions from practitioners that nobody's really thought through. And you guys are in a region with a lot of snow. Not everybody in the lower 48 will experience the same issues you do. So I would encourage you to ask those questions.
I think the next change that was brought into the newer code was this calculation for windward drift. Because previously, if we are looking at a similar size upper and lower roof, we would almost always find the leeward drift would govern, just because if you've got calculation for your windward drift being 0.7 of the leeward drift, and then the geometry ratio stayed the same, 1:4. In the newer version of the code, it does address that maybe we have to extend the drift length of the the windward drift from 1.4 to 1.8. So, which really makes this comparison of the two types of drift trickier. So as you can see, I did some quick illustration here. So those are sort of the comparison of the two types of drift from the two versions of the code, assuming we have the same thresholds for the upper and lower, right? And you can actually see that the overall volume of your windward drift increased from almost half of the leeward drift to now equal, but if not a little even higher than the leeward drift. But what's important is that the center of gravity of these two triangles do sit differently. So it really depends on how sensitive your structure is. And now it's going to be trickier for you to maybe load both of the drifts into a structure model and see which one is the governing case. The other thing is on the thermal factor part of things. I think in the 22 version of the code, we now have a more refined CT breakdown for the different roof insulation levels and the R values and the ground snow loads. I think on the roof insulation part, it's relatively easy to understand. When you have a higher R value, that means you've got less heat emitted from the roof. That means you have less melting, which would translate to an increased roof snow load. But this insulation layer will also be dependent on how much snow you have on top. Because like snow, the pack of snow itself also works as a layer of insulation. So a less snow, a less PG, which means you've got less insulation on top of the roof, and also again translates to a lower CT value. And I think from the chart, if you have a higher R value and the lower PG value, that's almost equivalent to you have a heated roof, which is basically a CT of 1.2. I think, yeah, so far, I think I've covered some of the major revisions in the snow provisions in the 722 And as I mentioned, I guess the whole purpose of introducing all these updates are really to, I guess, first more accurately predict the ground snow load distribution across the roof, and also try to acknowledge some of the uniqueness in local climate and how that would apply to your building geometry, which then is going to lead to your the snow distribution on the roof, right? But again, that's still code, and we know code tends to be a little conservative because it has to cover basically all types of building geometry, and basically trying to envelope the worst case in the provisions. And what if we want to see some of the more refined snow load based on your climate characteristics, or just how actually your building geometry is going to behave in the specific climate. And to do that, we have, I guess, a series of approach which could go all the way from a simple desktop calculation or desktop analysis to what we call a water foam simulation, and all the way up to a wind tunnel testing method. So the first one is what we call a parametric assessment of wind directionality. This is really because although the code has introduced this winter wind factor, it's basically addressing how windy it is in a specific region. It does not account for where the wind is blowing from. Say if you have, in this case, we've got a predominant winter winds from the north and the west. So if you have a step that's facing both of these directions, either of these directions, you will have the cold type drift. But what if your step is actually facing, say, the southwest or the northeast? It's not necessarily to actually form a full drift that code calculate. So we are able to look at the I guess wind directionality and assign reduction factors to it based on a desktop level. And if we need more refinement from that, then we can step to some of the physical model study, including, first of all, is the water plume simulation. So what the water plume simulation is really good at is to identify some of the more unique snow distribution pattern, I guess, complex roof geometries. So I think these are probably some of the patterns the code is not able to identify. And I think on the right, we're looking at Sky Dome, which is nowadays it's called the Rogers Center. It's the home of the Blue Jays baseball team. And it's when they were trying to design this dome structure, I don't think the building code back then had an idea of how we can really distribute the balanced loading across a arch or dome structure like this. So we were asked to do a little simulation of this unique structure in the water foam to visualize how snow could distribute across the roof, even the different winter wind directions, right? And after doing that, we can then make a step forward and then try to quantify the numbers through a more detailed study. And before I go to that more detailed wind tunnel study, a water foam simulation is also really good at looking at renovation of existing building. So for example, so for this project I'm showing on the left here, we are actually acquired by the owner of the new building, which is in the red right now. So if we're looking things just by code, where you have a taller building that's standing next to the gray building, the gray existing building here, we are going to have a pretty big surcharge on the roof of the existing building, which is just by code. But after we tested the two scenarios in the water foam, we're actually going to see that it's not really dumping snow directly from the roof of the new building, but it's creating this kind of unique and balanced loading scenario, which half of the existing roof could be scoured clear of snow, whereas the other half will be basically fully loaded. So those are some of the things we observed from a flume test like this. And after we feel there's a need to, I guess, quantify some of the numbers for the client, and then basically have some numbers that we can put in the structure model. And that's when we can start utilizing what we call a finite area element, the FAE method that the firm developed, I think, just when the Skydome was designed. So this FAE method is really a combination of your wind tunnel testing and your numerical computer simulation. So the wind tunnel testing part is what I showed on this current page, is really just to have this wind speed and direction sensor, which we call the SVV sensors. We're trying to use the sensor to install the sensor across the different areas of the roof. And by doing that, we are able to know that for all the different wind directions, we are able to know how actually wind moves across different areas of the roof. Say, you would have this corner areas, which we have this acceleration going on, but then you would have some of the more shorter area, which you don't have much wind speeds, which means snow is not essentially going to be moved around from that area. And so that is the wind tunnel testing part of it. It's really just to obtain the wind velocity information across the roof area of the building, right? And after we have that information, we are able to put it into a computer model. It's kind of similar to your finite area model, how you discretize your SEAAK or sort of themes and you do your stress analysis. We're basically using a similar concept here. We are discretizing the roof into the series of 2D cells. And from the previous wind tunnel test results, we would have the velocity information at each cell given if in wind direction, right? And then we would then combine the data with the past climate time history for the past, say, 50 or 70 years, which I think you can probably see from the time history here. I think it's getting a little blurry now, but we basically are able to use the wind speeds information, the wind direction, air temperature, solar radiation, cloud cover, and all the good things from the time history to simulate the snow accumulation on the roof, and then how snow is going to be drifted given a specific wind direction and intensity in that specific hour, and also given the solar radiation, your convective heating from the wind, and also this heat emitted from the roof. We're able to also track down the melting process of your snow. And if you got some melting going on in the snowpack, you've got more moisture content. The snowpack tends to be a little heavier and it's less likely to be moved around, and all those effects are taken care of. And what we do is that we do the simulation for each of the winter we have in the time history, maybe 50 or 70 years, and then we would work out a peak value for each of the load case, and then we do this extreme value analysis and try to fit into a accurate statistical model to work out a equivalent around 50-year design value just to match the code. Yeah, so that was just a quick rundown of the methodology of this method, and I think this is one of the examples where the FAE method was really able to take care of the effect of regional climate. I think the code is dealing with winter wind intensity, but what we're able to look at is both the directionality as well as things like temperature, how fast the snow can melt. I think for this specific project, we are seeing that this classic and balanced loading scenario to be formed on one side of the roof, but the same is not actually happen on the other side. So, but if you do it by code, the code will say you have to do this unbalanced action on either side of the roof, and then try to challenge your structural based on that. And you can see that from the comparison of the two time history here. On the left, we have the ground snow loading time history. On the right, we have the roof snow loading. And there is basically a pretty good reduction between the two graphs. And that's really considering how much snow can be scoured off the roof due to wind, and also how much snow can be melted. And the other thing I kept mentioning about the thermal effect. The other advantage of our modeling is we can actually look at the how snow is melted both from the heat emitted from the building itself and also convective heating that's brought by the wind, right? So I think this is a recent project we did where the client was trying to do some renovation work on their existing R12 roof. They're trying to see if it's okay to upgrade to R40 roof without having to do a bunch of renovation to reinforce the structure. So I think by using the code from R12 to R40, we're looking at something like a 20% jump in terms of the snow loading. But then if we're taking into account all the wind scouring and also the convective melting that's introduced by wind, I think the difference we're seeing from the R12 to R40, it's some of the, it's definitely lower than what code was suggested. And then I think they were quite happy about the values we provided. And they eventually went with the R40 roof. And the other side of things, excuse me.
While you're having a drink, Kenny, I think so a lot of these tools, they're not newly developed. We've been using them in Canada for probably 20 years. As Kenny said, some of them were developed around the Skydome project or the Blue Jays Stadium because the owners of that wanted to get a better understanding of how the structure is being loaded. So, things like load duration are considered in some of those by using the time histories of precipitation through the winter and the number of freeze and thaw cycles, get a much more accurate picture of what's happening in any given winter. And then we cycle through, a record of maybe 50 winters. Based on the extreme load buildups, we can calculate loads fairly precisely. So they're not new tools, but the American standard, it's fairly recent where we've been able to leverage some of these tools within the ASCE.
We've got a question there?
Yes, this is a question you might not want to answer, maybe can't answer, but I mean, how much does this cost to do? And I know that I've got experience working with you guys on a project, and whatever it was that you charged the owner was worth it because you showed that the code snow drift on an existing roof where we're putting an addition. Your study showed that the drift was much smaller, and so it prevented having to do very costly roof upgrades. But it's when we're trying to weigh options in the project, it might be difficult for us to kind of know when we hit that critical mass of, hey, we should call RWDI and have them do a study here. I don't know if you got any ballpark guidance.
Are we able to
just call you on a research basis?
Well, I mean, very roughly speaking, I would say fees are, in the $25,000 to $50,000.
I was going to say,
But the
I think the room is muted again. Hey, Kenny, we can't hear you online.
Which I think is addressed in the Canadian building code now, but not yet into the ASCE. So when you have a roof that's large enough, the wind is not necessarily able to scour the snow off the roof. It's really just pushing snow on one side of the roof, moving to just another portion of the roof without reaching to the edge of the other side of the roof, right? So that characteristics of larger roof with larger flat areas like this can be well captured by the FAE method. And for this stadium itself, we're also able to try to reduce the unbalanced loading that code would otherwise suggest us to do. And the other thing, yeah, so now this one is a classic sort of refinement and on the unbalanced loading scenario. So I think this is the Logan Airport in Boston, and they're trying to add this arched canopy in between the terminal and the parking structure. And by code, you would almost have to do a classic unbalanced scenario of it's basically taking the load away on either side of the roof and applying to the other side. But as you can see from this building geometry with the passing here, if wind is coming from the bottom of the page, yes, I guess wind is possible to push the snow on this side of the arch and to the I guess the leeward side of it. But if we have wind from top of the page, just because we've got a much taller massing of the parking structure, we shouldn't be seeing much wind movement on the canopy itself. And that's exactly what we found from by running our analysis. So this is the sort of unbalanced scenario we are able to capture from the FAE, which is you have half of the arch, which is this part of it, pretty much cleared of snow, and it's redeposited back to the leeward part of it. But we are not looking at a scenario which this part of the roof is loaded and the other half is unloaded. And this is the other, I guess, renovation project I mentioned earlier for the water plume, where we did identify a quite unique and balanced scenario where I guess this which the top of the top triangle area of this rectangular roof, it's basically scoured clear of snow, but the other half is still loaded. And just from the picture, without like you would almost say that from a conservative point of view, you would almost take the entire load from this half of the roof and dump to the other side. But that is just looking at the distribution from one single event, right? And I think one of the gentlemen just suggested, so what if we take the entire winter into account, because that's going to move snow around differently. And that's something that FAE is able to do. And after we do that, we did find there is a sort of unbalanced loading between, I guess, the two triangle areas, but the difference is really just a 0.2 kPa, which I think is around 4 PSF. So the client didn't end up having to do a reinforcement for part of the existing structure. And just, I guess, at a side note here, we're also able to utilize some of the more advanced computational fluid dynamics tool we used for the wind engineering side of things and apply it to the snow movement on top of the building. So I think that pretty much sums up the approach we take for building roof snow loading. I'm gonna be heading to the other snow issues like snow drifting and falling ice and snow. Before I do that, do we have any questions? Okay. And we still have time. Keep going. Okay, sounds.
Quick question.
Yeah.
You mentioned you thought there was an update coming to ASCE 728. Given to the lines on firm to buy what's.
Yeah, I think both Mike and Sihan are sitting on the committee for both the loading and the climate change chapters. I think, yeah. Mike, we're Sihan. Are you able to comment about that?
Sorry, can you repeat the question? I can only hear part of it. Oh, now I'm concerned we lost sound
Maybe
again.
do you want to continue? And
Yeah.
We'll see if we can get Mike back on to talk about that.
No,
That's your
I'm
question. Good.
sorry, I'm here.
Yeah, so what I've talked about so far was really just on snow loading on the building roof and utilizing some of the tools we have at RWDI. We can also look at how snow is essentially drifted around the building at grade level from a more of an operational and maintenance point of view. So for example, I guess you don't really want to see a big pile of snow that's drifted to the front of your main entrance. And those are some of the aspects we can look at either earlier in the design stage, which is what we prefer. You can really just change your building orientation and add small architectural features to avoid those problems. So those are some of the examples in a more urban or suburban built environment. And we also work on, highway studies. It's basically for if you don't start considering this aspect of snow drifting, you would end up having snow drift onto different part of the highway. And then we were also involved in some of the architect works, including some of the research stadiums that in the Antarctica as well. And these are just some photos of how we run the waterfront to basically have the building geometry tested in the waterfront and see if we have problems around the area. And if we do, how can we deal with them? And I think on the bottom right here, we're looking at a research stadium where we're asked to basically do a workshop of how far the building has to be lifted from ground to avoid some substantial drift at your entrance for staircases. And also, they're also looking at how far this building have to be spaced out. So each of the building is not interfering with each other in terms of creating snow drift that can be in front of the neighboring building. And here are some of the concepts we can sort of think about how to mitigate some of the ground level drifting issues. As I said, we always prefer early in the design stage, then we can really just play with the location of your building as well as the orientation of them. But then if we are at later of the design stage, we can still add features like sort of parapet or canopy or even some niche stuff like a wind deflector to really push snow away from the entrance. And in terms of highway, it depends on the wind directionality and the wind exposure. There will be necessary to either plant trees or dense forest or an artificial snow fence on the upstream side of the highway, just so that the snow drift potential can be captured before it reaches the highway. And here are some real world photos of some of the mitigations I talked about. On the left, we have this classic wind deflectors that's pushing snow away from the entrance down there. And in the center, we've got your waste building. Essentially, we're creating this channeling effect between the building and the ground and pushing the snow away from the building facade. I think this also would help with the snow entrainment into the building. And on the right here, you're looking at a classic snow fence that's really what it does is it's really trying to trap the snow particles right behind this fence, so it doesn't move forward and enters it. For in this case, these two snow fencers are installed further upstream of this village here. I think it's in the Hudson Bay area in Canada. It was designed like this, so bulk of the volume of the drifting snow can be captured before it reaches the village, so they don't have to deal with the same amount of maintenance work during a typical winter season. Yeah, and here just another look at how we can utilize the water forms simulation to, I guess, validate some of the mitigation strategies in terms of, say, adding a wind effector, or just also where it can be as big as changing our highway design. So we can try to minimize the scale of drifting that's going to be predicted on the highway. Yeah, and I think that pretty much sums up of how we can do what we can do for from a ground snow drifting perspective. And what we're also sometimes involved with is this falling, what we call it falling or sliding snow, ice and snow. So it can be from things as big as a curvy, slippery stuff like this, where it can also be resistance from pretty generic window sill and overhead soffit like this. So as I said, we always prefer to get involved early in the design stage, so that we can really just look at the overall design package, because there are really just little things that we can point out for the architect or the engineers to consider in the design, to be added in the design, to try to minimize some of the risks. But if it's later in this design stage, even after construction, some of the mitigation features will be much harder to be applied. And the next slide are two of the, I guess, the bigger project we worked on, try to help identify some of the sliding scenario, basically how much volume of snow it can be slide off the roof. And on the left, we have the Skydome Rogers Center in Toronto, Canada. And on the right, we have the Viking Stadium. So for the Viking Stadium, we actually both help them with first of all, determine how much snow there will be on the roof from both a structural loading standpoint, and also that information is going to help them to design this catchment area to allow there's sufficient capacity for the snow to go in. And I think John mentioned that there's some substantial structural steel saving on this one.
So that one, the snow studies, by reducing the unbalanced loading on the roofs and the balanced loads and the drifts, they saved about $8 million by just so you can lighten the roof structure, reduce the cost significantly. So the detailed studies had a big benefit. You got those sloped surfaces, the snow is going to come off of them at some point. I mean, you can try to retain it. That's one strategy, but a different strategy is allow it to slide off the roof, but you've got to allow for like a catchment area to prevent any issues with falling ice and snow or risks to people using the building or operations. So when you have a huge pile of snow going into those catchment areas, you also have to figure out how to drain those areas reasonably well, quickly. So there's a lot of work went into that particular.
Yeah, then the next slide is just how we can actually get these more unique architectural features tested in a realistic way. So we can actually send them into a climatic chamber and try to simulate the same sort of winter conditions for that specific region. Try to first apply some precipitation, very snow, frozen to the features, and we start trying to increase the feature. So you started melting from the bottom of snowpack. When you have a thin layer of water between your facade and your snowpack, that's when the snowpack is going to start sliding. And then we can actually try to work out the ideal slope of either try to retain sliding as much as possible, or just let it to be steep enough that you can slide as readily as it falls.
Kenny, you got a question in the back?
Yep.
I think we're running out of time here. We're gonna need to.
Yep. So I think this is one more slide.
Yep.
I think the last slide is probably something to also be interested. So some of the folks both in ASCE and also from our company have been worked on the climate change aspect of this, both the wind loading and snow loading. And this is a paper published by SEAAK, one of our colleagues at RWDI. So from his study, at least based on the more conservative climate change model, we are looking at an increase of both snow load and wind load in Alaska, especially for the northeastern part of Alaska. I think the magnitude of increase, at least for ground snow load, is roughly at 10%. Obviously, there's going to be more study to be done. But I think in the future version, the 28 version of the code, there will be a climate change chapter, and potentially some of those values will be presented over there as well. So yeah, I think that's pretty much the end of our presentation.
I did ask your question to our partner in Guelph, and he just wasn't able to unmute himself. But he said that the ground snow map for Alaska, there's an effort to update the values to be very similar to the contiguous United States for the 2028 version, but it's nowhere near 100% sure that's going to make it in that version. And then he said that there is a climate change, or like he's speaking to, that they're going to address for optional future condition chapter. There are proposals in there for wind, snow, rainfall, and ice accretion change factors for future in that as well.
Mike, is that you?
What's that?
Is that what you're?
Mike Gibbons.
Yeah, I don't, can you,
That answers
can't
your
hear me
question.
now?
Right.
Yeah.
Awesome. Thanks, everybody.
That's probably the end of the questions.
Thanks for coming up and doing your presentation. That's for you.
Thank you.
Everybody likes more water bottles.
Yeah.
Fill it with ice and take it through TSA.
All right, thank you.